Well, remember how much time it took us to go from when we first started to get into the derivative, get into applications of derivatives. We really did spend quite a bit of time. We had to go through the foundation, the building blocks of the limit. And well, the good news is in just a little over a week, we've gone from not really knowing anything about the integral to now in this lesson 13.4, which is the last unit in chapter 13, we are actually going to get rocking and rolling on finding the area under of a curve, the accumulation. And again, it's the area under a derivative curve. So that's, we're getting the area under a rate. So the function's giving us the rate of change. What happens is that's the accumulation underneath. So if you've got the rate of people coming into an event, that's in a derivative. And if you sum that, you get the total number of people that end up in the stadium. Something is like that. If you've got the marginal cost and you find that area, you can get towards the total cost, or at least the change of cost from one point to another point. So this is a very valuable business tool. And so let's just get right on it. We're going to look at, the Fundamental Theorem of Calculus. This is the basis for the integral, getting the area underneath the curve. It's a very valuable thing. And you're going to see if you followed along real well in 13.1, 2, and with the techniques of finding the integral, this will help build on that knowledge you built, as well as now we will actually have meaning. So we're going to go through the first part of this presentation. Is going to take a look at making that connection that what we did with Riemann sums connects with finding the integral, and that when we get the area underneath the curve, that really is the definite integral with two boundaries on it. Okay, then I will work through some problems at the end. I'll put them in a separate video so that you can get some practice with working through these types of problems. So first we'll talk about the connection, and this again is more of a higher level to get you to understand why. So it's valuable time, but don't get too much into the details because it's really just going to make that connection. Okay, so first of all, we're going to talk about being given a marginal cost function, right? So this is a marginal cost function. It is a derivative. And we're going to take a look at finding how much does it cost to go from producing 100 caps to 200 caps. And what we're going to find out, well, we'll find out what we find out. But this is what the setup is. The problem is a business problem is we know what our marginal cost is. And remember, that is what the rate of the cost is changing at. It's not the total cost. It's how the cost is changing to produce one more. So it's a derivative. And what we will do is if we find that antiderivative, we actually get the cost function. Okay, so from the marginal cost function, we integrate, and what do we get back to? We get back to the actual cost function. So just remember, when we integrate, we add 1 to the exponent, and this 4 is like x to the 0 power, so we add 1 to it. That's going to give us 4x to the first power over 1, which is just 4x. This, when we integrate, remember there's a 1 here, and what we're doing is we're integrating each term separately. We could do that because of the sum rule, sum and difference rule, right? So we're taking a difference here. So we add 1 to the exponent, that's going to give us an x squared. And then we divide by that new exponent, so it's going to divide by 2. So 0.001 divided by 2 is now going to be 0.0005 not divided by 2, but we've already done that. So let me write, you'll see it on the next page, but 4x minus 0.0005 x squared. And then again, we always had plus a constant. We're going to be able to drop this off because what we're going to be looking at is we're looking at this function from two different endpoints. Okay, and we'll just see how it works out. So here it is, 4x minus 0.001 divided by 2. Now they just leave it that way. That's fine. There they go. They took it divided by 2. There's our 0.0005 and plus a constant. So that's our cost function. So the cost to produce 100, we plug in 100 to the x values. That's all it is. This will give us our cost. Now, we don't know that total cost because the function we ended up has a possibility of having a plus k. But watch how this really doesn't matter when we are going to calculate from 1 to 200. Now let's calculate the cost. So do the math on this part. You get 395 plus some constant. Okay. To figure out the cost to produce the 200 caps, we go through the same process. We start with the function 4x minus this x squared, so we plug in 200 here, each of those, do the math, do the arithmetic, and we end up with 780 plus some constant. So the difference between producing 200 and 100, all we got to do is subtract the 2, because what, 385. And so when we subtract those two, 200 minus 100, that's the change in cost. Watch what happens. Here's a k here, but notice as this distributes, the k becomes minus. The k cancels out. It doesn't matter if k was 1,000,000, 2, 0. It doesn't matter. It's going to cancel. So we just get 380 minus 395, which ends up being an additional $385 to produce 200, going from 100 to 200. So that extra 100 costs us 385. The first 100 costs us 395 plus something. This one costs us just another 385. Kind of cool. Volume savings, right? Makes sense. So this is just getting us to say that the constant doesn't matter if k was 0, if it was 1 billion, 1,000,000, 1 trillion, 24, it's going to cancel out. So we could really use any of these functions. So we could use this one, which is plus 0, this one, which is plus 4. When we do our calculation, they are all going to give us the correct answer of 385, which is the difference in cost going from 100 to 200. So for these type of questions, we integrate. If we're given a derivative function, we can integrate it, and then that's what the Fundamental Theorem of Calculus tells us. We go from one end of the spectrum to the other, we plug those in and we subtract them. And I get assuming that the higher end goes first because that's what we need to subtract it from. Okay, so the process is starting with the derivative, find its integral, which is, in this case, the cost function. Look at the boundaries we're given, the interval. Then that change of cost is the area under the marginal cost curve. So another way we could have done it, we could have graphed the marginal, the derivative, found the area underneath the curve. We would have got the same answer. So this is the one thing you kind of have to keep track of, is which function are we using? Are we using the derivative? Or are we using the antiderivative? When we calculate these by hand, we use the antiderivative. When we calculate these graphically, we're going to see we use the derivative. So hopefully we can keep that part straight. So when we get this, notice here's the derivative function. We integrate it and we take it over its interval and we're good. But graphically, notice this graph here is the graph of the derivative. And so this is what we've been doing with Riemann sums. we get a rectangle, and if we got this area of this rectangle, we would be able to calculate as 385. So it's 100. It's got a base of 100, and it must have a height. Again, it's a changing height, so we'd have to. Well, let me show you how you could do that. It's a little bit earlier than maybe I wanted to get into it. So we're going to graph the derivative function for minus 0.001 x. That's the derivative function. Notice we're going to go from 1 to 200. Those are x values, so I'm going to set my window to go -1's okay. Let's go to 250. So I just like to go a little bit further. Now the y values, I don't know what we need to make our y maximums at. Let's see if 50 works. Okay, so we're just kind of guessing. I want to go to the graph. So I can see this. What I can see is I've got a lot of space up here. I'm going to come back and make my y max 10. I think that'll be plenty good. Okay, so there we go. And watch this. We've got a tool here called the Calc tool, the TI-84 does. If you have a different version of the calculator, different calculator, it probably has this function. We can look for it. So this is function number 7. We want to integrate. So you either hit number 7 or arrow down to it, hit enter. It will ask you what your lower limit is. The lower limit is 100. And then it asks for the upper limit. The upper limit's 200. Notice it fills in the area under the curve. It's 385, is going from 100 to 200. So now you're saying, Little Crow, if all we have to do is plug this in, why have we been spending all this time to find the integral? Now it's a math class, you got to learn how to do it. But also there's going to be situations where we need exact values, and I will work some of those in the homework. You actually will need to be able to take the integral to find the antiderivative, and then we will plug it in, because this is oftentimes giving us an approximate answer. In this case, the approximate and exact answer end up being the same thing. Okay, but that's a process we can go through. And you can see it's the area under the curve. Okay, and we did this. We found the function itself. We put in 200, 100. We subtract the two results. We got the 385. That is the fundamental theorem of calculus. So this next section, we're going to go through and we'll talk a little bit about the notation and move forward. And then we'll look at an example. But that's all we're doing. If you get the antiderivative, put in the upper limit, subtract the lower limit, boom, you got it. Sometimes we can use a calculator as well. Okay, so that's the fundamental theorem of calculus. And we got to there in one semester. Those who are doing the physics-based calculus, it takes them 2 semesters to get as far as we've gotten. So it's a good overview. Actually, I took both of them because the professor, again, I may have told you before, the professor at Portland State really helped me to understand math. I just started taking any class that professor taught. I took the physics calculus with him. I took brief calculus with him. I took business statistics from him. Anything he taught, I took it. And I'm good. That's, I learned a lot from him. Anyway. Statement of the fundamental theorem of calculus. So here's the formalized statement. Again, we've got a derivative function. We're going to integrate it. When we integrate it, we get capital F. We have limits of integration. That's the important part. Remember, when we started out, we didn't have any limits of integration. We just had some general indefinite integral. We now have a definite boundary. We have a definite integral. So when we've got that antiderivative, we plug in b to one end, subtract what the result is when we plug in a, and this result is equal to that integral, that definite integral. It is equal to the area under the curve of the derivative function. Okay, it's not the area under the actual of the capital F function, it's the area under the derivative function. Okay, and again, some math theory part, if we've got a continuous function and it's continuous on this integral, which means that the graph could be drawn without lifting your pencil, then there will be an antiderivative, and any of them will work. Remember, and what all that's saying is that the constant doesn't matter, because this part, you end up with k minus k or c minus c, which is always going to give you 0. So that constant part doesn't matter. That's all it's saying. And again, in words, if you want to read through it, that's what this is saying down here, just what we described. We're going to work through some examples. We'll see, integrate it, plug in the higher end, subtract what happens when you plug in the lower end, and that's going to give us our answer. So here's an example. Actually, there's a problem here. This capital F, I should have caught that, should be a little f, right? Because this is the derivative of this, 2x. So this really is, if you want to think of it, it's the integral of little f of x from 0 to 1, and it integrates into the big F. Okay. So when we do that, notice when we integrate, what we get is, if you were to do this, you add 1 to the exponents, you get x squared divided by 2, but then you still got this 2. 2 divided by 2 is 1. So what they're doing is, I guess it's down here, you're getting x squared minus x squared, and notice they're plugging in the upper limit. So there's the upper limit, the lower limit, 1 squared minus 1, and there it is. Okay. Again, we could go to the graphing calculator, take a look at it to make sure it works, and I'm just going to do that to emphasize what we're doing. So what we're graphing is the derivative function. So here we graph 2x. I'm going to change our window because I know what we're just going from 0 to 1, so I'm going to go from -1 to 2. I like to give a little bit of extra space so you can see what's happening. And I just know we'll probably be fine from -1 to 10. Probably don't even need that far. We're going to graph it. So going from here, we see what we got. And again, we're going from 0 to 1. So we use this tool, calc, number 7. We put the lower limit, which is 0. We put the upper limit, which is 1. And we get the area under the curve is 1, just like all that went on here. So this is what we're having. But again, the thing to focus on, what did we graph? We graph, let me back up. What we graphed is the derivative itself. We did not graph the x squared function. The x squared function, what we did is we used that to do the calculation by hand. Okay, so that's kind of one of the things to kind of keep in track, is we've got two different functions. We've got the derivative and the antiderivative. We use the antiderivative for by hand calculation of plugging it in, subtracting. We use the derivative function for graphing and getting the area under it. Okay. Here are some examples. You can use it with piecewise functions. We're not going to have you do any of these, so I just left it in there just in case you wanted to see it. So now let's go to one more example. And just briefly, how do we integrate this? Well, remember, this is like the integral of 1 minus the integral of x squared. So this integrates, this is x to the 0, add 1, divide by 1. This integrates to x, add 1 to the 2. So that's going to be x to the 3rd divided by 3 plus a constant. So that's what it's going to integrate to. We'll let them walk through it, and they sort of did it, but not as with much explanation. X minus x to the 3 over 3 plus a constant. Okay, so that's what we've been working on before. That's the antiderivative. That is the underderivative, as sometimes I call it. It's the capital F function instead of the little f function. But since we are looking to go from 0 to 1, what we do is we take the function at 1, subtracting the function at 0. And when I'm saying the function, I'm saying the antiderivative function. So they're going to go ahead and plug in 1 to this, 1 minus 1. So you get 1 minus 1 over 3. That comes from this part. The last part, when you plug in 0, you get 0 minus 0, which is 0. Okay, so this was the second part. So we do the calculation, 1 minus 1/3. That's going to give us 2/3. I'll click the button, and there it is. Again, we come back to our graphing calculator. We can graph the derivative function. I'll clear this out. 1 minus x squared. That's the derivative function. We're going from 0 to 1. I think we're okay with our window's still okay. We could come down a little bit if we want. Let's do that. Let's make the y be just 4, and we'll get a little bit better view. We are going from 0 to 1, so I go second calc, and I come down to number 7. Now this one, it's when you calculate by hand, you put the upper limit in first and the lower limit in second. When you use the calculator, it's all backwards. You put the lower limit in first and the upper limit in second, and then you see the window. It's 0.66667, which rounds, that's the decimal equivalent of 2/3. Okay, so you see it, the area under the curve. I just want to emphasize it's the area under the derivative curve, and we were able to find that same value by taking the antiderivative and plugging in the two ends. Okay, so that is our lesson. That is our lecture section. I'm going to hold it off here. Then I'm going to look at some application. Oh, no, I'm a little ahead of myself. Let's go. I'm going to walk you through this application. Then I'm going to work some homework problems. This one we'll just kind of click through. You can see this is again oil spilling into the ocean, which is a terrible thing. But this is a rate function, so this is a derivative, and it's valid for the first 20 days. So we've worked with this one before. If we integrate it, which we do here, we can go from 0 to 20 days. Remember this, I think we started this in 13.1. No, 13.3. I think we did this as our Riemann sum calculation. And if we go from 0 to 20, notice it's been integrated. We plug in the 20, we plug in the 0. The 0 wipes everything out, so that's kind of nice. This is all gone, and so we're not subtracting anything. We just have these three items, and we calculate each of those, and then we got 613.3 barrels. And if you wanted to look back at the Riemann sums, I think we were getting closer and closer to that by taking finer and finer Riemann sums. But this is the exact value. Well, it's an approximation because it is rounded. It's probably a repeating 3, right? Yeah, because of this one, repeating 3s. But that's how we're going to go about it, is we can actually, instead of having to take all these multiple Riemann sums, we just integrate it once, calculate two values, an end value and a beginning value. Go back, and that will give us our answer. We also could have graphed not this function. If we were going to do this graphically, remember, let's get all the way back there. We would have had to graph the derivative function, and then we would have found the area under that curve from 0 to 20, and we would have found that it was this value. Okay, and I'll let you do that. What we're going to do next is take a little break, because you should shake off the cobwebs of all this that you've learned, and then I'm going to make another video showing how to approach several of these homework problems, because some of them, they want the exact value. So you can't just plug them all into the calculator, but some of them, they want the approximate value, and we'll look for that word approximate. approximately how many. And then we can use a calculator, and I'll show you both ways of solving those problems to help you work through the homework. There's quite a few problems in this section, but it was pretty light, with only 4 problems in the Riemann sum. So take a little break, and we'll be back.